Hello everyone, and welcome back to our security design principles uh, course. So, like we discussed last time, there are 10 principles overall, and in order to keep it engaging, like in this video, we will focus on principles 1 through 5. These are what I will refer like as the core secure design principles, which they focus mainly on how to design system to be secure by default, okay? Starting from the architecture and access control. So this is going to be the content of this video, okay? And here we go. So we start with the first secure design principle, which is minimizing the attack surface area. So every time a programmer like adds a new feature to an application, they also increase the risk, including a security vulnerability. Okay, so each feature creates new way for users and also for attackers to interact with the system. So the attack surface refer to all points where an attacker could potentially interact with or exploit an app. Okay, so by maybe minimizing the attack surface area, developers restrict the functions that users are allowed to access, and this is mainly the main purpose. Like this reduces mainly the number of opportunities an attacker has to find, or I said, to exploit any weakness related to that app. So the main goal is to remove, I would say, useful functionality. No, it's not that. Okay, it's not to remove useful functionality. Be careful. But so think of it. What is the main goal if we are, I would say, minimizing and reducing the functionalities? The main goal is to expose only what is necessary. Okay, and nothing more. Okay, so if I want you to learn something mainly from this first principle, is that whenever you have more features, there is more risk. Okay, and in secure design, few entry points usually mean, let's say, fewer security problems. Okay, so mainly, or let's try to really understand this idea a little bit more, the idea of minimizing the attack surface. So we first need to define what attack surface of an application actually is. So the attack surface includes, I would say, all paths, okay, where data or commands can enter or leave the application, okay? So this includes, let's say, things like input forms, like API, like the network connections, the interfaces exposed to users, or even like to other systems. Okay, so it also includes, I would say, the code that protects these paths, like for example, authentication and authorization mechanisms, activity logging, data validation, and encoding. So in addition, let's say the attack surface also includes, I would say, all valuable data used by the application. So this can include, let's take some examples. We have here like secrets and cryptographic keys, intellectual property, critical business data, personal data, and personally identifiable information, or PII. So finally, it includes, I would say, the code that protects this data, for example, such as encryption, checksums, access, auditing, and other controls that ensure data integrity and operational security. So when we talk about reducing the attack surface, we are not just talking about reducing features, okay? We are talking about carefully managing access points, sensitive data, and the mechanisms that protect them, okay? So here probably the main takeaway is that the attack surface is bigger than just features or just code. Okay, this is what we need mainly to keep in mind. So the image here is a great illustration of what we mean by attack surface. Here, what we have, the application um, is a mobile device, but mainly the idea is can be applied to any system. Okay, so here, like each labeled area represents a potential entry point where an attacker could interact with or exploit the system. Okay, so for example, we have access to location data, SMS messages, emails, and calendar information. Each of these handles sensitive data, okay? And let's say as a result, expands the attack surface, okay? We need to think of it this way. So on the network side now, we see network attacks, we see also browser attacks, and we can also see cloud applications, which here introduce kind of external communication paths into the system. We also see the malicious apps like sensor malware and even hardware related attacks, like, for example, the SIM card or NFC. Okay, so the important takeaway here is that every feature, connection, or interface adds, I would say, to the feature surface. So this way, the principle of minimizing the attack surface is so important. The more exposed, I would say, components a system has, the more opportunities an attacker has to find a weakness. Okay, and in short, let's say that when we talk about attack surface, it's, I mean, all the ways in, okay? Let's look at a simple example to make this principle more concrete. Now, imagine an application that includes search feature. On the surface, a search-like feature seems harmless, okay? But in practice, it can be, I would say, a valuable, okay, source for attackers. Like, for example, we can think of attacks like file inclusion attacks, or SQL injection attacks. If in case like we have that, it is not carefully designed, this like search feature. Okay, so one way to reduce the attack surface is to limit access to that feature. First of all, like for example, we can think that instead of allowing anyone to use the search function, the developer could restrict it, and so that only registered users are able to access that. Okay, so by doing this, the number of potential attackers is for sure reduced, and the risk of successful attack is also lowered. Okay, this is a practical example of how minimizing the attack surface helps improve security without removing functionality. And really, the core idea here is that limit who can access features to reduce risk. Okay, so keep this in mind. The idea is to limit who can access features in order to reduce risk. And let's move on to the second secure design principle. And the this one is establish secure defaults. Okay, so this principle states that in an application must be secure by default. In other words, when a new user starts using the system, okay, the safest things should already be in place. If a user wants like higher privileges or fewer security restrictions, they should have to actively take steps to request or enable them, assuming that is like even allowed in that case. Okay, so secure defaults apply to many aspects, I would say, of an application, such as they affect how user registrations are handled, how often passwords must be like updated and how complex passwords need to be. So while some users may be allowed to turn off certain security features, these features should always start at, I would say, high security level by default. Okay, so this approach mainly reduces the risk of accidental misconfiguration and protects users who may not be security experts. Okay, and the overall idea here is that security should be by default and it's not optional. Okay, uh, now this screenshot is a good example of what secure defaults look like in practice. Okay, so in this example, what we have, when a user, let's say, is asked to change their password, the system does not have security decisions up to the user. Okay, instead, it enforces some specific requirements by default. Like, for example, the password must contain, like we see here, few requirements like minimum length, like include uppercase, lowercase, like include characters, numbers, special characters, and so on. Okay, so the user does not have to decide what a strong password is in this case. The system defines that for them. So while users may be allowed to change their password later, or I would say they can even use password managers, but the default behavior is secure. Okay, we are making sure that the behavior by default is secure. And this is exactly what the principle of establishing secure defaults is mainly about. So it's about protecting users even when they are not security experts. And the core idea in this context is good systems protect users automatically. Okay. Moving now to the third secure design principle. This one is mainly the principle of least privilege. So the least privilege design principle. So this one often is abbreviation of POLP, okay? P for principle, O for O, L for least, P for privileges, okay? So the POLP now states that the user should like be given, I would say, the minimum set of privileges like required to perform a specific task, okay, and no more than that. Exactly, we give him like what they need. Okay, so for example, if we have, let's think of a blog application, a user who is registered as an author should not be having the administrative like privileges. Okay, that user should be able, okay, to create and edit their own articles, but they should not be allowed or able to add or remove other users or change system. I would say, for example, make any like system-wide settings changes and so on. So by limiting, I would say, the privileges in this way, we reduce the potential damage. It like if an account is, for example, compromised or misused. So the principle of least privilege applies not only to users, but to resources and to system components, okay, throughout the whole like web app, okay. So in secure design, access is always granted based on necessity and not based on convenience. Okay, so the core idea again in this third principle is that give only what's needed, nothing more. Okay, and the fourth secure design principle now is known as defense in depth. So this principle mainly states that the best way to secure an app is to use multiple security controls, each addressing risks in a different way. Okay, as you can see in this like picture, we have many layers. Okay, and this is the idea that I want you to just think of it. Okay, one lock is not enough. So instead of relying on a single security mechanism, defense in depth uses layers of protections, like having multiple layers of protection. And for example, let's think of rather than like allowing a user to log in with just username and a password, the system might also use an, like for example, IP check that is possible. Also, like in our like university, there is the geo verification, or there is also the system like we call the captcha system. There is also the logging of login attempts and brute force attack detection and so on. So these are multiple techniques, and we can discuss like one of them later. We'll discuss mainly the captcha system. Okay. So now, if one security control in this case fails, like, or it's, I would say, bypassed, the other layers can still help protecting the system. Okay, so the layered approach makes it harder to attackers to succeed, like, and increases the overall like resilience and security of the application. Okay, so this is mainly the idea. Again, like one lock is not enough. And now moving on to the CAPTCHA. So CAPTCHA is a common, I would say, example of defense in depth used in many applications. So its goal mainly is to distinguish between human users and like automated programs, such as bots, for example. Okay, so in this example here, the text is distorted and slightly modified. Okay, so that it's mainly difficult to a computer to understand or interpret the letters in here. So, but still, it is readable, I would say, from a human, like for a human. Okay, so the idea is that CAPTCHA systems have like received many criticism. Okay, so especially, let's say, from people with disabilities, sometimes it's difficult, like, to write it correctly. Even I personally don't like it that much, because it's people even, and I'm sure many of you think that it wastes your time, it's difficult, it's like sometimes impossible to solve and so on. Okay, so we all maybe experienced this with the captcha. um, they also criticize it by like if someone is using it, I would say, all the time in their everyday work, it's going to slow down things by having like to read distorted text each time. So I would say on average it takes about 10 seconds for a person to solve a typical captcha. Okay, so, and despite these all issues, I would say captcha is still widely used. We can see it like in many apps. And the main reason is that it's used as an additional layer of security. It's somehow efficient, and not only to protect, like just like protection mechanism. Okay, it's one of the layers. And so the core idea here is that CAPTCHA is a security layer, and it's useful, but it's not the perfect. It's not that perfect, okay? So this is just an example. Now, in this diagram, what we have classic way to visualize the principle of defense, I would say, in depth, okay? So instead of relying on a single like security mechanism, security is implemented here in multiple layers, each protecting the system in a different way. We see the different colors like of that layers. And now we start from the outer layer, which is the red layer. Okay, so mainly like here we have policies, procedures, and awareness. So these include things like data classification rules, password policies, of, I would say, code reviews, and so on. Even human behavior is part of security. Okay, so moving inward to the orange layer, we see the physical security, such as, like, we can think of locks, also badges, guards, the physical access controls as well. So this is the idea. Next, in yellow, yeah, we see the network, or I would say, or perimeter layer. And this one includes firewalls, includes encryption, and protections against denial of service attack, okay? DOS. So instead that, like we have also in green, in purple, sorry, or blue, the host layer, okay, which forces on like mainly the idea here is the focus on operating systems, patching, I would say, malware detection, protection, and so on. Then comes like in purple the access control, okay, in the application layer where we have the authentication, authorization, the secure code practices, and like access control are enforced, okay? And at the core, like we have the data security. Data security protects databases, sensitive information, also message level security. And the key idea here is if one layer fails, I would say the other layers are still there to reduce the damage and protect the system. So the main takeaway is security works best when it's layered, okay? Now, the last one for this video, the fifth like secure design principle, is known as fail-safe defaults. So a real system failures happen all the time, and a database like connection may fail. So a network request also may fail. A user may enter incorrect data, and this can happen many times, okay? So this principle states that when failure occurs, sorry, the application should, I would say, fall or fail in not like in a secure way, okay? So in other words, a failure should not never give a user additional privileges or access they did not already had, okay? So it should also not, I would say, reveal sensitive information, like for example database queries, error logs, or internal system details. They must not be shown to the final user if only, like I would say, a failure is happening. And from a security perspective now, it is always safer to deny access by default when something goes wrong rather than allow like it, okay? So failing safely helps preventing attackers from gaining useful information or from like unintended access, I would say, during error conditions, okay? So mainly the main idea I would say here is when things break, security should not break with them, okay? And this is the concept of, so mainly, so here we have just an example in this image. So it shows, I would say, simple but very good example of fail, I would say, safe defaults. So the idea here, we see this fifth principle in action. And let's see now, when a user tries to enter, let's imagine or think of an incorrect password. So the system respond, I would say, and with a generic error message, like you see here, your account or password is incorrect, and if you don't remember, it said. So here this prompt does not show information, and it does not tell the user whether the username or the password was wrong, okay? So it does not like reveal any internal system details. So this is important because error messages themselves can leak information. By keeping the message now general like this one, the system avoids giving attackers like what we call clues, okay? And there is no hints for attackers, okay, that can or could like be used to guess, I would say, a valid username or exploit the login like process. So this is exactly what failing securely principle means, okay? When something goes wrong, the system denies access and reveals as little information as possible. Okay, so with this example, we have completed the first, I would say, security design principles, the fifth five, I mean, first, and the second video is also done now. These five principles we're discussing in this recording form the core secure design principles that focus on building systems that are secure by default. And in the next video now, we are going to continue with the remaining principles. So we see last far there are 10. 5 are covered now. 5 we're going to cover in the next video. And these 5 will focus on more on trust, on human behavior, real world systems, like the interaction. And so mainly these are left for the last part. Now, errors should protect the system, okay? Not expose it. Just keep this in mind. And thank you so much for watching. And so, see you in the next video.